This is the fourth and final part of the virtual lecture for January 8th, 2015. We're going to be revisiting our 5 Pigeonhole principle problems and see just how beautiful a simple idea can be. Problem 1. We had our 805 lockers in the athletic facility and a lot of students trying to use it. The question is, how many students must share a locker? I like to specify my pigeons and my boxes. In this case, the 4,026 students are playing the role of the pigeons, and the 805 lockers are playing the role of the boxes. And we are assigning students to lockers, pigeons to boxes. By the generalized form of the pigeonhole principle, we're placing the 4,026 objects into the 805 boxes, so the conclusion guarantees that some locker must have at least the ceiling of 4,026 divided by 805. That ends up being 5 and a little, but because we're taking the ceiling function, we round up. So the conclusion is that 6 students, there must be a locker that contains at least 6 students. That is a lot of sharing going on, and hopefully that's not happening at our new YMCA. I think problem 2 is very beautiful. No matter what 101 integers you choose from between 1 and 200, there will always be a pair of them that evenly divide. The pigeons in this case are the 101 integers that are somehow chosen from the set 1 to 200. Boxes, it has to be something clever that forces divisibility, and ideally, since we have 101 pigeons, we're probably looking for 100 boxes of some form. Now, I don't expect you to come up with this clever idea on your own the first time through, but I hope you appreciate it. So let's label the boxes by all the odd integers between 1 and 199. There happen to be exactly 100 of these. That sort of makes me have a warm feeling in my heart. So I've labeled all the boxes with the odd integers, 1, 3, 5, 7, up to 199. And here we have sort of the random in the middle kth box, which has to be odd. So of all the 101 integers that you've selected, place an integer, n in this case, let's call it integer n, into box k if n can be written as a power of 2 times k. That we call k the odd part, or you could think about it as the largest odd factor that divides n. Just as some examples here, so in the box that contains 1, we're going to have 1, 2, 4, 8, 16 if they happen to occur. In the box that contains 3, you'll have 3, 6, 12, 24, and in particular in the box that contains k, whatever the odd integer k is, you'll have k, 2k, 4k, 8k, 16k, until you get to a number that is just less than 200. The good news is we're assigning 101 integers to 100 different boxes, so there must be a box that contains at least 2 integers by the simplified form of the pigeonhole principle. Those 2 integers, by construction, have been designed so that the smaller number in the box will divide the larger number. That's because the odd parts of the integers is exactly the same, and one of them has a smaller power of 2 than the other one. So that means no matter what 101 integers you choose, 2 of them will have to divide one another. Erdős and Zakaras. This is a very, very beautiful theorem. So let us start. For each element in our sequence A sub I, determine the length of the longest increasing subsequence that begins with that element. So here I've created just a simple subsequence of length 5. So A1 is 7, A2 is pi, A3 is -1, A4 is 101.1, and A5 is -1. So for each element in this sequence, we want to figure out the length of the longest subsequence that starts at that number. It's easiest to do this beginning from the end of the sequence. So A5, if I start at -0.5 and I move from left to right, I can only create a sequence of length 1, period. If I start here at A4, which is 101.1, and I'm looking for an increasing subsequence, I cannot, if I move from 101.1 to -0.5, I don't increase. So again, the longest subsequence that can be created starting with 101.1 is going to be 1. Now, if I look at A3 and I start at -1, I'm looking for an increasing subsequence. So my subsequence could be A3, A4, because I'm increasing from -1 to 101.1. Or it could be A3, A5, because in fact I'm increasing from -1 to -0.5. But in either case, the subsequence has length 2. Beginning at A2, the longest increasing subsequence you can create is also 2, namely starting at pi, increasing to 101.1, and that's all you can do to increase. And starting at 7, to increase, we have to go to 101.1, and again, I have a subsequence of length 2. So we have our small example here so you understand what's being asked. But for each number in the subsequence, you're going to label it by the length of the longest increasing subsequence that starts at that number. If we got lucky and one of these subsequences that was created gets a label of n+1, then you have a subsequence that's increasing of the right length. We did not get lucky here. Our example is n equals 2, so we're looking for a label of 3, which we don't get. Okay? So instead, I claim we have to go use the pigeonhole principle. The pigeons are the n squared plus 1 real numbers in the sequence that we picked, so A1, A2, up to a n squared plus 1. And the boxes are going to be labeled with these length numbers. And these boxes are going to be labeled 1 through n because we did not get one that was as large as n+1. If we had the n+1 label, we'd be done. So all of our labels lie between 1 and n. Using the generalized form of the pigeonhole principle, we have n squared plus 1 pigeons being assigned to n boxes, and then we divide and take the ceiling. That means I'm going to end up with n+1 numbers in some box. Okay. Look at our example. Here we have n+1 is 3. I have 3 numbers, each with the same label 2. So those are the 3 numbers in the same label. What do you notice about this sequence? It's 7, pi, -1. That's a decreasing sequence of length, in this case 3, but in general it will be of length n+1. So I'm not going to do the details, I'm going to leave them to you to think about how you could show that the n+1 numbers given the same label have to form a decreasing subsequence, and that's going to complete this problem. This is the classic party problem. Given 3 arbitrary students, show that there are either 3 mutual friends or 3 mutual, that better be strangers. Okay, 3 mutual friends or 3 mutual strangers. Begin by giving our students names. We could call them A, B, C, D, E, and F, but I prefer to give them the names Alice, Bob, Carol, Dennis, Eve, and Frank. Next, you have to pick one of the students to distinguish, and I'm going to choose Bob. This will help us decide our pigeons and our boxes. The pigeons will then be everyone but Bob. So that leaves 5 of them, namely Alice, Carol, Dennis, Eve, and Frank. The boxes are going to be decided based on their relationship with Bob. Either box 1 is going to contain the friends of Bob, and box 2 is going to contain those people who are unknown to Bob, so they are strangers to him. By the generalized pigeonhole principle, we're starting with 5 objects, distributing them to 2 boxes. So we know the conclusion is some box will contain the ceiling of 5 divided by 2. That's a ceiling of 2.5, which is 3 rounding up, people. So there are 2 cases that are happening here. Case 1 is that there are at least 3 friends of Bob. Case 2 is there are at least 3 strangers to Bob. So consider case 1, where Bob has at least 3 friends. If any pair of his friends are actually friends themselves, so that they would be mutual friends, then if you take that pair, let's say Alice and Dennis here, that pair plus Bob would be 3 people that are all mutual friends. Otherwise, Bob's 3 friends don't know each other at all, and they would form 3 mutual strangers. So in the case when Bob has at least 3 friends, either way, we're going to get 3 mutual friends or 3 mutual strangers. We just don't know which one for sure. Case 2 is where Bob has at least 3 unknown members, so rather than being friends, they would be strangers, and the argument is going to work similarly. This time, if any pair of Bob's unknown people are also unknown to each other, we would get a mutual triple of strangers if we included that pair in Bob. Or all 3 people in the box would have to be friends of one another, and we would get 3 mutual friends. So regardless of whether you're in case 1 or case 2, we always have to wind up with 3 people that have the same mutual relationship, either friends or strangers. So the theorem holds. Our final problem for the day. Given 10 arbitrary students, show that there are either 3 mutual friends or 4 mutual strangers. The problem is going to start exactly the same way. We pick a distinguished student who's going to help us distribute people to our 2 boxes. So everyone but Bob this time will be our pigeons. And since we started with 10 people, Bob is one of them, we will have 9 pigeons in the group. And the boxes again will be friends of Bob and people unknown to Bob. This time, rather than filling the boxes evenly, as we did in the previous example, we're going to use the strong pigeonhole principle and have slightly different target levels. So for the friends of Bob box, we're going to look for a fill level of 4 people. And for the strangers of Bob box, we're going to look for a fill of 6 people. And now we're going to use the strong pigeonhole principle. Notice that if you take Q1 plus Q2 minus the number of boxes, which in this case is 2, plus 1, we get 9. That's the number of people we're distributing. So we're distributing 9 people into 2 boxes. So according to the strong pigeonhole principle, there will either be 4 people in the Friends of Bob box or 6 people in the box who are unknown to Bob. So our 2 cases are going to be a little bit different this time. In case 1, assume that Bob has at least 4 friends. As we saw before, if there is a pair of friends in the box, then you take that pair of friends plus Bob, and that will make 3 mutual friends. Otherwise, everyone in the box has to be mutual strangers, but that means there are now 4 mutual strangers. So if Bob has at least 4 friends, we know the pattern we're looking for of 3 mutual friends or 4 mutual strangers has to occur. But what if Bob doesn't have 4 friends in the room? That means there have to be at least 6 strangers to Bob, 6 unknown people to Bob. But if that happens when we have 6 people in the room, by the problem we just finished, that means there will either be 3 mutual friends, in which case we're already done, or there will be 3 mutual strangers. And in the case of the 3 mutual strangers, take those 3 strangers, consider them along with Bob. They're all strangers to each other, which means there are now 4 mutual strangers. So regardless of whether we're in case 1 or case 2, we end up with 3 mutual friends or 4 mutual strangers. And that really shows the power of the pigeonhole principle. This concludes the presentation. I hope you will get together for class on Tuesday and work through some problems. If you don't, spend the time working through problems on your own. I will prepare more videos for Tuesday's class. Look for them soon. Work hard.